Well, thank you to the organizer for inviting me here and to speak about our QUAX proposal, which is the query axiom or quest for axions. So it's another experiment looking for axiom as a main component of the dark matter. So it's an analogoscope, but in this case there is a different ingredient. That means that we wanted to do something different from ADMX or the other new experiments that are being proposed right now. And the idea is that in our case we want to look to the axiom exploiting its axion-electron coupling. In fact, unfortunately, this is present only in one class of axion models, which is the DFSZ. And because, for example, the other big class of axion models that is known is KSZ. In that case, the axion doesn't couple to fermions, but it does, but it's strongly suppressed. It's about a factor of 1,000 smaller, the coupling. For DFSZ axion, you have an effect Lagrangian, where the coupling to the fermion is mediated through this gamma 5 Big matrices, and so you have a coupling constant which is related to the mass of the fermion and the axion decay constant. At the end, this turns out to be a dimensionless parameter, which is again very small for axion masses in the range that we are interested in. If you look to the non-relativistic limit of the electron equation of motion, you can see that you have this term. And you can identify this term as the form of a spin magnetic field interaction, where the magnetic field, you can recast this part over here like this. So you have just the spin of the electron with the Bohr magneton, and then a magnetic field equivalent part. This magnetic field is exactly given by the presence of an axion gradient. So you need a gradient of the axion field. And if you have a gradient of the axion field, then you can have an interaction with the electron. And so the effective oscillating field, magnetic field due to the axion, will have a frequency which is proportional to the axion energy, and the amplitude which is proportional to the axion density. So how do you have what is the idea, the scheme of the scheme principle of the idea? Since we need to have interaction with electrons, with electron spins, you need matter. If you need matter, then you suppose that you have some, and since you have to look for interaction with the spin, normally you can do this if you have some matter that you can magnetize. You can magnetize this matter through an external magnetic field. So if you have some, say, this is some matter that you put inside the magnetic field. If you put it inside the magnetic field, then you can have this Zeeman splitting of the ferromagnetic transition, and you can select through the amplitude of the static external magnetic field a Larmor frequency transition. The axiom is coming actually, is present in the dark matter halo of our galaxy. There is just static. However, since the Earth with the solar system is moving through the dark matter halo, you will see then a gradient of the axion field. And this is just what we used to call it an axion wind. So the axion is behaving like a wind, which is interacting with your electrons in the matter, and is interacting in the form of an effective magnetic field. This is for the frequency, for the masses that we are interested in, so it means in the few microelectron volt up to a millielectron volt mass range, the frequencies are in the gigahertz regime, and this is why this is normally called a radio frequency magnetic field. This is a radio frequency magnetic field. So the idea is that the axion then interacts with the electron spin, and it changes the total magnetization of the material. These changes in the total magnetization can produce a real now magnetic radio frequency signal, electromagnetic radio frequency signal that can be detected through a sound detector. Here you can also already see that all the system is actually placed inside a micro resonator to get better sensitivity. I will explain you better afterwards. This idea is actually not came from us, it's rather old. It came out in the 80s and then beginning of the 90s through these authors. However, we are just trying for the first time to devise a real experiment to look for this to devise a real experiment using this scheme. And so we, in a paper, we just made our proposal. You can see it here. And let's see what are the numbers now that are important. So you can calculate the effective magnetic field associated with this axion wind. And there's, of course, proportional to the axion density and to the Earth velocity through the dark matter halo. And of course, to mass and the coupling constant of the axion and the coupling constant to the electron. The number comes out, let's take some reference mass for this calculation, for example, 200 micro electron volts. The effective magnetic field, radio frequency field induced by the axion, is 2 × 10⁻22 Tesla, which is really a very small number. Just to tell you, very sensitive magnetometer at the moment are measuring something like 10 to the -18 Tesla. So we are thinking of the experiment to push the magnetic field sensitivity to a very, very low level. Of course, this is not a real magnetic field because it's an effective magnetic field induced on a sample. For this mass, the corresponding frequency would be just detected by the mass of the energy, which is corresponding to the mass of the axions, is the thermalized axion. And for 200 microelectron volt, you get 48 gigahertz. As for the photon coupling, and you have to identify what is the coherence of your apparatus for this detection scheme and the correlation length. And since we are dealing with the gradient of the axion field, this number is a little bit different from the one obtained for the normal axion field. And in fact, it's a little bit smaller, but still of the same size. So this means that your experiment cannot be bigger than 5 meters, otherwise you will lose signal in a sense, because your axion in the dark matter halo, the axion are just distributed with random velocity. So this is the axion signal is some sort of stochastic signal, and this is defining the important parameter for this stochastic signal. So a length of about 5 meters and a coherence time of about 10-20 microseconds, depending on the mass. So how are we going to detect this oscillating magnetic field due to the axion? As I told you, the basic principle is the same of the electron spin resonance. So you have a material with ampere electrons that can be, and with their spin can be oriented through an external magnetic field. So the external static magnetic field align the magnetization, so the total magnetic field induced due to the spins, which is described by the magnetization, and the magnetization can precess around the static magnetic field. This precession can be kept on resonance through the presence of a radio frequency field, which is in a plane orthogonal to the external magnetic field. So this is a static field, B0, which is defining the frequency of precession, and you can keep this precession on by the presence of a radio frequency field. Of course, the system is resonant, so it can emit and absorb radiation in this at radio frequency. And the frequency of this radiation is determined by the amplitude of the static field through the gyromagnetic ratio. So for 1 Tesla field, the resonance will be at 28 gigahertz. And so there is a experimental geometry that has to be fulfilled. So you have to have a static magnetic field in a z direction, supposed. And this defines also the normal resonance frequency through its amplitude. And then you have a radio frequency field in the orthogonal plane. These are, you can see here, you have a source magnet for the static field. You have, for example, a radio frequency cavity, which provides the radio frequency field. This is, for example, a sketch of the radio frequency field, how it's placed inside this cavity. This is a TM1020 mode, 102 resonance mode. And this can excite the PR transition, but also can detect the presence of changes in the magnetization on the same frequency may be induced by the axion. All the dynamics of this setup is described by a set of coupled nonlinear equations due to Bloch, which they describe the evolution of the magnetization vector M of the material. These are the Bloch equations, in fact, that they describe how the magnetization vector, which is the magnetization density proportional to the spin density, evolves in the presence of radio frequency field and static field. There are important parameters here. It's not just want to tell you that there are. The problem is that relaxation times in your system, because the amount of signals is related to the coherence of your system, and there are relaxation time. Three different types. One is the spin lattice relaxation time, and then normally called T1, which says how much energy goes from the magnetization dynamics into the lattice. Then there are spin relaxation time. That's actually is really the coherence time of your material. In fact, it determines the line width. And there is another time which is called radiation damping, which describes the interaction of your system with the environment. These are important because these times are the key times to calculate the signal strength. And these are typical values for this tau 1 or tau 2. And while the magnetization that tells you how many spins you are using. And again, this magnetization is important because it tells you that, again, the strength of the emission of radiation from the sample. And in a paramagnet, normally the number of spins available depends on temperature. So, using the Bloch equation, you can really calculate how much is the change in magnetization that can be induced on a sample due to the axion wind. And this is the result. So again, you have the magnetized sample inside the static magnetic field, and you somehow pick up this radio frequency emitted by the fact that your magnetization is changing. And the radio frequency is emitted through this form. I mean, if the magnetization changes due to the presence of the axion wind, this will produce a power. The system will absorb energy from the axion wind and then re-emit this energy as electromagnetic radiation, and possibly this can be detected. And this is the power that we are looking for. And so this is the MA over here, which you see that it's important. There are some constant factors, dynamic relation, Bohr magneton. Then there is the axion effective field, the number of spin in your sample, the density. And then there is this minimum time, that's the coherence time, on resonance, of course. And these are the choice between these three things. So the axion wind coherence that we've seen before, the material relaxation time, and the radiation damping. This is the one thing which is very important, because if you stay in free space, actually, radiation damping is an important issue. Sorry. Radiation damping describes how the system is related to the environment. So, for example, if I'm driving circuit, radiation damping is related to the Q of your oscillator, which is probing the radio frequency in the sample. But also is due to the emission of radiation. So, if you have, for example, in free space, a large magnetized sample, and you try to excite it, this can really decay in just emitting radiation, and this decay is described to this radiation damping mechanism. And you can see here that, for example, here you see that your power depends on the volume of the sample and the total magnetization, which is the number of spin. But the radiation damping time is actually the opposite. So if you increase the magnetization and the volume, you will reduce the radiation damping time. So you will kill your signal in a sense. So and this is really, if you go to frequency above 10 gigahertz and for large magnetization, this time is really limiting your signal. This is of the order of nanoseconds. So we have to devise a scheme in which to take away this radiation damping mechanism. And we can do that. The idea is to put our sample inside a resonant cavity and to couple the ferromagnetic resonance of the sample to the microwave cavity resonance frequency, the cavity of the resonator. If you do this, for example, this is a typical magnetic material that we are using. This is an X sphere, so we put something more afterwards. And then you have a resonant cavity, and we put the sphere inside the resonant cavity. And you couple the two together. When are you coupled them together? When the resonance frequency of the cavity and the resonance frequency that corresponds to the ferromagnetic, there are more frequency of the sample, are the same. When they are the same, and if the coupling is sufficiently strong, so that means that you have enough number of spins, the two systems, I mean the two oscillator hybridizes together. And what you see in a plot where you're describing, for example, this is the steromagnetic field which is changing the Larmor frequency. This is this plot over here, and this is the cavity resonance frequency. This is a transmission plot of this kind of setup. So if you are injecting some radio frequency, you are measuring the output through two antennas. And you see that when your Larmor frequency approaches the cavity frequency, you have an anti-crossing. So the two, what is happening actually is that your single resonance that you should get here actually gets split into two. And this separation is proportional to the amount of spins that you are using, so to the coupling between the two systems in a sense. But what is important is that if you look now at how can you describe the resonance of these hybrid modes, we call it. So the modes that are a composition between the cavity mode and the ferromagnetic resonance. You can see this description, and the line width of this mode is not affected anymore by the radiation damping term, which is just entering into which is just only frequency shifting the hybrid mode. So when you hybridize your resonance frequency inside with a microwave cavity resonance frequency, you get rid of the radiation damping mechanism. And this is very important because this was the minimum, this was a very small time, and then we get rid of this. It's just, you can think of this like that if you put your magnetic material inside this resonator, you are limiting the phase space for emission of radiation. And so somehow you are saying that this can emit radiation only with the characteristic time of your cavity. And so radiation damping time effects are eliminated, and the actual line width of your hybrid mode is actually related to the average between the cavity mode and the natural type T2 of the ferromagnetic resonance. From now on, always saying line width, relaxation time, Q factor, always with mixing them together, because more or less you're always defining the same thing, because the line width is the inverse of the relaxation time. The Q factor is just this ratio over here. So now we can try to calculate what is the expected signal that we have for our setup. And again, since we got rid of the radiation damping mechanism, we can put in a power that we measure some minimum time which is related to the properties of the material or of the cavity, say about 2 microseconds. We put the usual reference mass, 200 microelectron volt. That means that we are using a magnetizing field static of about 1.7 Tesla, 48 gigahertz. Say a reasonable volume, 1/10 of a liter. And this is the typical spin density that are for this Ig material that you saw before. And this is the power that we got. This is 4 10 to minus 26 watts, which again is a very small number, but probably not so small that cannot be detected. Of course, it cannot be detected using linear amplifier. This is not out of the reach of linear amplifier, but it might be detected at some point if you have a single photon microwave detection device that can work at this frequency. This is not available yet, but there are many people working on it, and we are collaborating with them. We are trying to see, and we hope that this will be available within 1 or 2 years, perhaps. This will mean, in fact, that you have a signal photon rate which is of the order of milliards. Of course, that depends on the background of this detection. One thing that will help us to do the experiment is that since we are sensitive to the effective field, this radio frequency field is determined by the motion of the Earth through the dark matter halo. The radio frequency field has a well-defined direction. And this direction has to be orthogonal to the direction of the static field that we put on our setup. Due to this, and since the Earth is moving daily and annually with respect to Vega, which is where the solar system is moving in the dark matter halo, there is actually a strong modulation of the signal, and this can be useful because we can have systematic studies in our apparatus. And this is, for example, for a single day, this is how the signal pattern should be, and of course this pattern is moving through the year. Of course, what we hope is that at the end, the real background are thermal photons, and then you can put some numbers to see how much you need for this background to be there, and you get out that the working temperature of the system should be below something like 100 millikelvin, which is feasible. And if we take these numbers, we'll have, say, a useful bandwidth of about 150 kilos measured in a few hours. So one now has to demonstrate that this R&D program is feasible. And these are the experimental challenges that we have to fight. So they are divided into this section. So magnetic material has to have a very high spin density, which is rather, this is already feasible, but it's not feasible to have this density together with such a large volume and sharp line width. Then you need, again, we need microwave cavities, which should have the same Q factor of the axion, which is of the order 10 to the 6. And the key point is that you should get this high Q factor inside the static magnetic field, which is not trivial. And of course, it must house 100 cubic centimeter of samples. Then for the magnetizing field, we don't need very high magnetic field because this is just used to tune the Larmor frequency. But it has, so not higher than 2 Tesla, but it must be really uniform and high stability at the ppm level. Otherwise, you will have an inhomogeneous broadening of the line width. Of course, then we need the signal photon counter, and we need to see how the apparatuses work all together when we put all the things together in a system at cryogenic temperature. These are our current laboratory setups. We have an old cryogenic system with an external magnet at room temperature in Legnano. Then recently we got a 4 Kelvin cryostat, which is housing a superconducting magnet, again in Legnano. This is nearby Padova. And then there is another group working with us in Frascati, where they have a superconducting magnet in a standard cryostat working at 4 Kelvin, where they are testing properties of the microwave cavities in the magnetic field. All these systems work with liquid helium, so we are at the moment just running at 4 Kelvin. And a dilution refrigerator is on the way, in the sense that we have an old one and we are trying to repair it. During the R&D phase, we are working in the 10-15 gigahertz range. Actually, the measurement I will show you are exactly at 14 gigahertz. So, the magnetic material. As I told you, you need a high spin density and a sharp line width. A good material, which has been studied already from the 50s, which is actually a synthetic material, is Ig. Ig stands for yttrium iron garnet. It's a ferrimagnet and with this chemical composition. And normally it comes in spheres. I'll tell you why. And in spheres which are highly polished. So this was studied in the 50s because having a sharp line width and resonating with a fraction of a Tesla fields, it was used for RF filters and using synthesizers. Oh, 5 minutes, okay. In a synthesizer in the 50s. And we tried, all people use it in room temperature, but then we started to study it at low temperature. We discovered, for example, that there are properties at low temperature that are not conserved. For example, the line width, but it can be better if it is a high purity Ig sample. Sorry, I have to go fast now. One issue is that if you put your Ig sample inside the cavity, of course, these spheres that has to be highly polished to keep the line width very thin. Then you have to collect a large volume by using several spheres. And we have demonstrated that you can put several spheres inside a single cavity. And then what you can see, since the number of spins scales with the volume, of course, then you have to see that your separation in the coupling that you see, that the hybrid modes that we were discussing before, when you have the anti-crossing between the two oscillators, this anti-crossing is much more separated but the higher the number of spin. Actually, it scales with the square root of the number of spin. And we have demonstrated this just using 1, 2, or 3 spheres, and then we didn't see any effect in the line width, which is good. So now we are trying to check other material because we still need to have a larger volume and a sharper line width, actually. And we have actually problems with the procurement of Ig, and we might start to produce Ig sphere by our own. For the cavity, resonant cavity geometry, we are using, we studied a cylindrical cavity geometry which is excited on TM110 mode. In this mode, the radio frequency field is actually orthogonal to the cylinder axis, and it is constant in this direction. And the radio, resonance is determined by the size of the plate. So you can really have this size how long as you want without changing the resonance frequency of the mode. And so we can fill up with material over here without in a zone of uniform radio frequency field. The external magnetic field, static field, which is produced in the Larmor transition, can be put in this direction. So it's a very convenient geometry. And okay, and this is, we choose this because we can really, in this way, increase the volume of the cavity for the insertion of Ig material. This I will skip. There is one important thing for the cavity, that the cavity has to be operated in a high, with a high Q factor, and but it has to be operated in external magnetic field. So normally people, for example, IDMX uses copper cavities. The copper cavities are limited to Q factor, which are not in excess of 10 to the 5. But we need something like 10 to the 6. So our idea is to try to use superconducting cavities, for example, now with titanium, where the critical field is above the field that we need. Since we need only 2 Tesla field, this can be done. Of course, there will be some degradation of the Q factor, but we hope that it's still possible to reach the 1 million Q factor. There is only one problem, that we need to be sure that the field is penetrating inside the cavity, otherwise it won't magnetize the material which is inside. And you will have, due to the Meissner effect, you have currents that are limiting the magnetic field inside the cavity. So to avoid this, we started to work with geometry which has cuts along the side wall of the cylinder. In this way, you are not permitting the Meissner effect to appear, and then you put also on the top plates, some copper plates, so that the external field can really penetrate. And this is, for example, a solution that we have built. So there is a copper cavity which is patterned with some niobate titanium, and there is a conical end caps to get a better Q. And with this cavity, they were working on 0.5 Tesla field with already a much better Q factor than the copper, just the copper one. But we are improving this setup. 0. Okay. Just sorry, I'm too long, but I wanted just to. I
think well, you can take a few more minutes.
Yeah, I take. Okay. Then we studied the magnetic field and homogeneity. This is our current magnet. But what I wanted to show you that we are trying to do. We have an improved setup now, the more recent setup, where we are working inside this cryostat with a cylindrical cavity at 14 gigahertz of the geometry that I showed before. We put inside these 5 spheres of GAIG, which is a little variant from IG. Actually, it's just with some gallium impurities. And we have a very good amplifier, but linear amplifier still, and a highly uniform magnetic field. And this is, for example, the hybridization that we see at 0.5 Tesla, corresponding to the 14 gigahertz Larmor frequency. This is details of our setup. For example, the spheres are here and are placed inside the cylinder, just with this Teflon holder. The sphere has to rotate because they have to align to the external field. This is our detection chain. And again, the detection strategies is very similar to the one employed by EDMX, because we're still looking for excess power on a single beam of in a power spectrum coming from the cavity with a very sensitive electronics. And so we tried just already to do this run. And for example, you see this is the power that we are measuring at the moment. You see on a certain bandwidth, this is about a fraction of a megahertz bandwidth. We're just running on a single frequency for the moment, just to check the sensitivity of the apparatus. And then we look for residuals to fact if there is any peak coming out from the flat noise, which is almost flat noise. This is due to nonlinearities in the amplifier. And so this is our current sensitivity. The idea is that this is the axion-electron coupling. This is the axion mass where we are sensitive, and on a very small bandwidth, because now we are really checking only our sensitivity. We can put some limits on the axion-electron coupling, which are truly, I mean, orders of magnitude way off from the models, but these are the first limit in this parameter space that are obtained from the experimental search for axion as the dark matter component. And so I think this is important to show, and we have now to demonstrate that this technique is worth it. This is the result has been obtained with these numbers, and by next year we should go to this. And if this is still working, then we will propose an experiment with these numbers. And with this number, we might be able to reach then the DF-Z model. As I told you, this is 1-2 more years for define the R&D program. And if the goals are fine, then we can get the numbers for the complete apparatus. Thank you, and sorry for the late time.
We have 10 minutes for questions. So.
Yeah.
I think it may have been on your slide, but I didn't catch it. The Q of your sputtered cavity was 150?
150,000.
But did that change when you put it in a magnetic field?
With the magnetic field, it was a little bit less. Up to 2 Tesla, we got 110,000.
110,000.
Yeah. And we are still working on it, in fact, because we expected to have, without the magnetic field, a much larger Q. We are not sure about the quality of our niobate titanium alloy, and how it was, whether the sputtering was the right procedure to put it there or not. And so I think that because, for example, with the same cavity on a lower frequency mode, which is actually the DMX mode, we had 1 million Q. And when we put the magnetic field, it kept up to 200,000 with the 2 Tesla field. So we believe that this is a good idea, and if we find the right alloy for the sputtering, then we can really get up to 10 to the 6 Q factor in the field. In the field, which is not a strong field for us. I mean, we don't need to go, of course, to 7, 8 Tesla, because even if we run at 48 gigahertz, this will be 1.7 Tesla. And there we hope that the degradation of the Q factor is not so strong for this type of market.
I mean, you probably also had it on your slides, but how do you tune the sensitive frequency again?
Yeah, there is there are 2 types of tuning. One, of course, we can employ it, but it's not been studied yet. We are studying it, just doing the same as IDMX is doing, with some tuning rod inside. But there is one other tuning that it is possible in our setup, which is for a small frequency range at least. That is the fact that if you look at this plot that I showed before, where you have the magnetic field and the frequency. And of course, the cavity is fixed there, and then this is the Larmor frequency. This is the region where you work. But this, you can have coupling between the two oscillators, even if the frequency are not exactly the same. And if you move, for example, a little bit the external field defining the Larmor frequency just away from the cavity frequency, you will get this. In fact, one color is for the perfect matching. Then you move from the perfect matching, and you can move the hybrid peaks. So, and this is a tuning in the sense. Of course, if you start to move a lot, then you will lose signal. But there is a band where you can move a little bit the field, have some tuning without changing anything in your apparatus. And this is, in fact, this is why in our limit that we have now, we already have a little scan in a sense, because these were actually, each of these are a single frequency measurement, and these are different scans that have been performed.
So this niobium titan is also used for the X-cell cavities, for the Tesla cavity, accelerating cavities.
Might be, yes.
I think they developed this method of electropolishing to get the high Q. I mean, they reach this 10 to the 6, I think.
What frequency are you using those there?
These are also gigahertz.
Gigahertz, that's right.
Gigahertz.
As I told you, up to 10 gigahertz it was fine. Above 10 gigahertz hours was giving us problem. But
okay. But they had this. So I remember. So I mean, so the design they should reach. So for the accelerating cavity, they should reach 40 megawatt per meter or something like that. And then they invented the method of electropolishing.
Okay.
And so maybe you can find some.
Yeah.
So at DC they have developed all these methods.
One of us, actually, Davide Alvesini in Frascati, is making all these ideas about this, and he's working on accelerating cavities.
Yeah.
And he's actually working now with the project in Romania to build a laser accelerator there.
Yeah,
which is similar to
Eli.
Okay. So he should know at least.
Other questions?
Okay, so thank you again.
Okay.